You ever stop and think about how an email you send from, say, New York somehow finds its way to a server in Tokyo in like less than a second? It feels like magic, right? Well, it's not. It's actually this brilliant system of digital navigation, and it's all run by routers. They're basically the traffic cops of the internet. So today, let's take a look at the rulebook they use to direct all that traffic. So, this gets us to the central question, the big puzzle. Think of the internet as this massive, sprawling city where roads are constantly closing, new highways are popping up, and traffic jams just appear out of nowhere every single second. How in the world do you give directions in a city like that? Well, that's the exact problem that routers have to solve every millisecond of every day. In the very early days, you could try something called static routing. That's where a network admin, a human, literally has to program every single possible route into a router by hand. Now, for a tiny network with maybe 3 or 4 computers, okay, maybe. But for the internet, with millions of routers and paths changing constantly, no way. It's absolutely impossible. That would be a full-time job for every single person on the planet. And that leads us to the ingenious solution, dynamic routing. The core idea is beautifully simple. Instead of us trying to tell the routers where everything is, we just let the routers talk to each other and figure it out on their own. They build their own maps of the internet, and, this is the crucial part, they update those maps constantly. Okay, so the first major family of these protocols, and a protocol is really just a set of rules for how to talk, is called distance vector. And the absolute best way to get how it works is with this brilliant little analogy, routing by rumor. The whole process is actually surprisingly simple. Just picture routers as people living in a town. Router A tells its immediate neighbors, hey guys, I know how to get to these streets over here. Its neighbors hear that, they add that info to what they already know, and then they turn around and pass the combined news to their neighbors. This rumor, this piece of routing information, just spreads from one router to the next until pretty much everyone has a complete, even if it's secondhand, map of the entire town. So, how did these early protocols decide which rumor was the truth? Which path was the best? The logic was incredibly simple. They just counted the hops. A hop is just any time your data has to pass through a router. So if one path takes, say, 3 hops and another one takes 10, the 3-hop path wins. Fewer hops means a better route. As simple as that. Now, this system sounds pretty clever, right? It seems to work. But here's the crucial question, and this is where our story takes a really dramatic turn. This whole thing is built on trust, on rumors. So, what happens if a router starts spreading misinformation? What happens if the rumor is just plain wrong? Let's paint a picture here. Let's say a network cable gets unplugged. Router E knows right away that it can't reach network 5 anymore. But its neighbor, router C, it hasn't gotten the memo yet. So before router E can spread the bad news, router C sends out its regular update and it says, hey everybody, I can get to network 5 in 3 hops. Router E hears this and thinks, whoa, router C has a path? Awesome. But what it doesn't realize is that router C's path is back through router E itself. And boom, just like that, a routing loop is born. This is one of the classic, catastrophic failures of early networks. Any data that's trying to get to network 5 gets sent from E to C, and C, following its bad info, sends it right back to E, which sends it back to C forever. The data is completely trapped, and the network can just grind to a halt. This creates this absurd problem called counting to infinity. See, every time that trapped data packet makes a hop between the two confused routers, its hop count goes up by 1. 4 hops, 5 hops, 6, 7. It just keeps climbing and climbing with no end in sight, eating up the router's memory and bandwidth until something finally breaks. So yeah, this was a huge problem. But thankfully, network engineers are a very, very clever bunch. They didn't just scrap the whole system. Instead, they came up with a set of really simple, elegant rules to stop these catastrophic loops before they could spiral out of control. All right, solution number 1 is a bit of a brute force approach, but hey, it works. You can call it the give up rule. Protocols like RIP just set a maximum hop count. Usually it's 15. If a packet's hop count ever hits 16, the router just assumes it's stuck in a loop and gets rid of it. It just drops the packet. This puts a hard limit on that whole counting to infinity nightmare. Now, the next solution is way more elegant. It's called split horizon, and it's basically a rule of polite conversation for routers. The rule is simple. Don't tell me what I just told you. So if router E learns about a network from router C, it will not, under any circumstances, advertise that same route back to router C. This simple piece of logic stops those 2 router loops we just talked about before they can even get started. And the third big solution is all about being proactive. It's called route poisoning, or my favorite, the spread bad news fast rule. When a link fails, the router doesn't just quietly stop talking about it. No, it actively sends out a new update telling everyone that route is now unreachable. It does this by advertising it with an infinite metric, a hop count of 16. This poisoned route update spreads like wildfire, making sure every router in the area knows that path is dead, which stops them from ever trying to use it. So when you put them all together, these rules made routing by rumor a strategy that actually worked. They made the early internet stable enough to function. But even with all these clever fixes, those early protocols like RIP, that stands for Routing Information Protocol, they were still pretty basic. They had their limits, and the internet was growing incredibly fast. So naturally, the protocols had to evolve. We went from RIP version 1 to RIP version 2, and that was a really significant upgrade. RIP v2 was just plain smarter. It could handle more flexible network addresses. That's called classless routing. It sent its updates more efficiently using something called multicast, instead of just shouting at every single device on the network with a broadcast. Oh, and it even added some basic security with authentication. This was a totally necessary step up for the internet at the time. But the real leap forward, the game changer, came from a whole new way of thinking. Instead of just relying on those rumors from your neighbors, a whole new category of protocols called link state came along. With link state, every single router builds its own complete identical map of the entire network. They all share info about who they're directly connected to, and then each router independently runs a calculation, usually an algorithm called shortest path first, to figure out the absolute best route from its own unique perspective. It's the difference between asking a stranger for directions versus having a live, up-to-the-second GPS showing you the entire state. So what's the big takeaway here? It's that the incredible reliability we expect from the internet, it's not magic. It's the result of decades of brilliant, step-by-step problem solving. The whole thing is built on these automated conversations happening between routers, all governed by a few simple but powerful rules that prevent total disaster. It's a system that is constantly evolving to get smarter, faster, and more robust. And that kind of leaves us with a final thought, right? We've gone from simple hop counts to these complex full network maps. As our digital world gets exponentially more complex, with AI, the Internet of Things, and speeds we can barely even imagine, what new languages, what new rules of the road will our routers need to learn next to keep this whole thing running?